Pluto, the dumbfounding planet living at the external edges of our nearby planetary group, is stirring up excitement within the vast neighborhood. Reports exhibit a potential encounter with Neptune, raising concerns among scientists and space enthusiasts alike. Renowned experts, including Neil deGrasse Tyson and Michio Kaku, have sounded alarms about the possible outcomes of this celestial conflict. But how did Pluto end up on a collision course with its distant neighbor? And what could this endless crash mean for us here on Earth? Let us analyze this unfolding event. Once considered an obvious planet, Pluto was later reclassified as a dwarf planet due to its unusual orbit. Despite this change, it continues to enchant and attract space experts. Continuous analyses from esteemed researchers highlight a concerning proximity between Pluto's orbit and that of Neptune. These experts caution against a potential collision between the two planets, posing a significant risk to Earth. Pluto's journey around the Sun is marked by its extraordinary characteristics within our nearby planetary group. Its orbit spans an astonishing 248 years, and since its discovery in 1930, Pluto still hasn't completed a full revolution. Adding to its intrigue, the incredibly elliptical shape of its orbit is a departure from the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted at 17 degrees to the ecliptic plane, making it more inclined compared to other planets. One notable feature of Pluto's orbit is its intersection with Neptune's path. For about 20 years in each orbit, Pluto ventures closer to the Sun than Neptune, challenging assumptions based on their relative positions in the solar system. So, why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational forces exerted by other planets. The study of Pluto's orbit began shortly after its discovery, presenting a perplexing challenge for astronomers. Unlike most planets whose orbits align relatively close to the ecliptic plane, Pluto's unique features include a steep inclination and an eccentric orbit. The mystery deepened with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit amidst these complexities serves as evidence of the intricate nature of celestial mechanics. The three-body problem in space involves calculating the movement and gravitational interactions among three celestial bodies, such as Pluto, Neptune, and the Sun. This problem explains the intricate interplay of their orbits and gravitational forces. Terms like libration and the Kozai effect help unravel this celestial mystery. Astrophysicists argue that libration, responsible for maintaining planets in their orbits, plays a crucial role in the Pluto-Neptune system. This term refers to the fact that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune, effectively preventing potential collisions. Libration ensures that when Pluto approaches Neptune or other giant planets, it is primarily aligned above their orbital plane, offering an additional layer of security against impacts. The Kozai effect explains why Pluto's orbit around the Sun appears irregular, but remains stable over time despite apparent anomalies. Numerical simulations in the late 1980s revealed that despite its consistent properties, Pluto's orbit is technically chaotic, with slight initial deviations leading to significant changes over long time frames. However, Pluto's remarkable orbit maintains stability over extraordinarily long timescales, keeping chaos within bounds. Continuous virtual simulations have improved our understanding of how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path near the Sun. Neptune's unique relationship with Pluto, completing 3 orbits for every 2 of Pluto, contributes to the stability of Pluto's orbit. Furthermore, Jupiter's massive gravity exerts a significant influence, while Saturn's impact, although smaller, also plays a role. Through extensive studies, scientists have demonstrated that the combined effects of Neptune, Jupiter, and Saturn ensure the protected and stable movement of Pluto in space for billions of years. These phenomena are vital for maintaining the order and consistency of celestial movements in the universe. Without these mechanisms, the solar system would be prone to greater chaos, potentially leading to collisions or ejections from stable orbits with far-reaching implications for other celestial bodies. Understanding Pluto's orbit is particularly crucial in discussions about a potential collision with Neptune in the future. This knowledge provides a clearer understanding of the dynamic nature of the planetary system. Pluto's case highlights how seemingly unstable orbits can achieve equilibrium through the intricate interaction of gravitational forces and orbital mechanics. Ongoing observation and analysis of these phenomena are essential for gaining a better grasp of our position in the universe. Exploring the depths of space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit serves as a perfect example of this unpredictability. The nature of orbital mechanics vividly demonstrates the delicate dependence of a celestial body's path on its initial conditions. As shown in Pluto's case, even slight variations in the dwarf planet's position or speed can significantly alter its long-term orbit. Automated simulations have been instrumental in helping scientists understand how Pluto moves in space. By making small adjustments to these simulations, space researchers can observe how even minor changes can have a substantial impact on Pluto's trajectory. In the late 1980s, these simulations uncovered an intriguing aspect of Pluto's orbit. Despite factors like libration contributing to its stability, Pluto's orbit can still exhibit irregularity. Even a small initial difference in Pluto's position or speed can lead to massive changes in its orbit over many years. Nonetheless, despite this inherent turbulence, Pluto's orbit remains stable for such a long time, spanning billions of years. This suggests that beneath its seemingly chaotic appearance, Pluto's journey around the Sun follows an organized order. Predicting celestial events and forecasting the future paths of heavenly bodies, especially for planets like Pluto with unusual orbits, is incredibly challenging. The inherent unpredictability of these systems makes long-term predictions uncertain. Numerical simulations help us understand and estimate the future movements of celestial bodies, but they also reveal the limitations of our predictive capabilities. These models heavily rely on precise initial conditions and replicate complex interactions, where even a small error can lead to drastically different outcomes, making accurate predictions difficult. The chaotic nature of celestial orbits, like Pluto's, reminds us of the ever-changing universe. While we have made progress in understanding space, Pluto's case highlights our ongoing limited knowledge. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the planetary system. It demonstrates how the presence and position of each planet can affect the stability and direction of other bodies in the system. Despite these complex forces, eminent astrophysicists are expressing concerns about a potential collision between Pluto and Neptune. Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our planetary system, particularly regarding Pluto. Tyson, known for reclassifying Pluto as a dwarf planet, shares insightful thoughts on how our understanding of celestial mechanics is continually evolving. Tyson sees Pluto's reclassification not as a demotion but as a necessary adjustment in light of our growing knowledge about the various objects orbiting the Sun. His approach to celestial mechanics involves constant learning and adaptation. Tyson believes that the allure of these mysteries is what makes astronomy so fascinating.